Helium is the chemical element with the atomic number 2 and is represented by the symbol H, lowercase e. It is a colorless, odorless, tasteless, non-toxic, inert, monatomic gas that heads the noble gas group in the periodic table. Its boiling and melting points are the lowest among the elements, and it exists only as a gas except in extreme conditions. An unknown yellow spectral line signature in sunlight was first observed from a solar eclipse in 1868 by French astronomer Pierre Janssen. Janssen is jointly credited with the discovery of the element with Norman Lockyer, who observed the same eclipse and was the first to propose that the line was due to a new element which he named helium. In 1903, large reserves of helium were found in the natural gas fields of the United States, which is by far the largest supplier of the gas. Helium is used in cryogenics, in deep-sea breathing systems, to cool superconducting magnets, in helium dating, for inflating balloons, for providing lift in airships, and as a protective gas for many industrial uses such as arc welding and growing silicon wafers. Inhaling a small volume of the gas temporarily changes the timbre and quality of the human voice. The behavior of liquid helium-4's two fluid phases, helium-1 and helium-2, is important to researchers studying quantum mechanics, in particular the phenomenon of superfluidity, and to those looking at the effects that temperatures near absolute zero have on matter, such as superconductivity. Helium is the second lightest element and is the second most abundant in the observable universe, being present in the universe in masses more than 12 times those of all the other elements heavier than helium combined. Helium's abundance is also similar to this in our own Sun and Jupiter. This high abundance is due to the very high binding energy per nucleon of helium-4 with respect to the next three elements after helium: lithium, beryllium, and boron. This helium-4 binding energy also accounts for its commonality as a product in both nuclear fusion and radioactive decay. Most helium in the universe is helium-4 and was formed during the Big Bang. Some new helium is being created as a result of the nuclear fusion of hydrogen in all but the very heaviest stars, which fuse helium into heavier elements at the extreme ends of their lives. On Earth, the lightness of helium has caused its evaporation from the gas and dust cloud from which the planet condensed, and thus it is relatively rare. What helium is present today has been mostly created by the natural radioactive decay of heavy radioactive elements, thorium and uranium, as the alpha particles that are emitted by such decays consist of helium-4 nuclei. This radiogenic helium is trapped with natural gas in concentrations up to 7% by volume, from which it is extracted commercially by a low-temperature separation process called fractional distillation. Section 1. History. Section 1.1. Scientific discoveries. The first evidence of helium was observed on August 18, 1868, as a bright yellow line with a wavelength of 587.49 nanometers in the spectrum of the chromosphere of the Sun. The line was detected by French astronomer Pierre Janssen during a total solar eclipse in Guntur, India. This line was initially assumed to be sodium. On October 20th of the same year, English astronomer Norman Lockyer observed a yellow line in the solar spectrum, which he named the D3 Fraunhofer line because it was near the known D1 and D2 lines of sodium. He concluded that it was caused by an element in the sun unknown on Earth. Lockyer and English chemist Edward Frankland named the element with the Greek word for the sun, helios. On March 26, 1895, British chemist Sir William Ramsay isolated helium on Earth by treating the chemical cleveite, a variety of uraninite, with at least 10% rare earth elements, with mineral acids. Ramsay was looking for argon, but after separating nitrogen and oxygen from the gas liberated by sulfuric acid, he noticed a bright yellow line that matched the D3 line observed in the spectrum of the sun. These samples were identified as helium by Lockyer and British physicist William Crookes. It was independently isolated from cleveite in the same year by chemists Per Todor Cleve and Abraham Langet in Uppsala, Sweden, who collected enough of the gas to accurately determine its atomic weight. Helium was also isolated by the American geochemist William Francis Hillebrand prior to Ramsay's discovery, when he noticed unusual spectral lines while testing a sample of the mineral uraninite. Hillebrand, however, attributed the lines to nitrogen. His letter of congratulations to Ramsay offers an interesting case of discovery and near discovery in science. In 1907, Ernest Rutherford and Thomas Royds demonstrated that alpha particles are helium nuclei by allowing the particles to penetrate the thin glass wall of an evacuated tube, then creating a discharge in the tube to study the spectra of the new gas inside. In 1908, helium was first liquefied by Dutch physicist Heike Kamerlingh Onnes by cooling the gas to less than 1 Kelvin. He tried to solidify it by further reducing the temperature, but failed because helium does not have a triple point temperature at which the solid, liquid, and gas phases are at equilibrium. Onnes's student, William Hendrik Kessem, was eventually able to solidify 1 cubic centimeter of helium in 1926. In 1938, Russian physicist Pyotr Leonovich Kapitsa discovered that helium-4 has almost no viscosity at temperatures near absolute zero, a phenomenon now called superfluidity. This phenomenon is related to Bose-Einstein condensation. In 1972, the same phenomenon was discovered in helium-3, but at temperatures much closer to absolute zero, by American physicists Douglas D. Olshershoff and David M. Lee, and Robert C. Richardson. The phenomenon in helium-3 is thought to be related to the pairing of helium-3 fermions to make bosons, in analogy to Cooper pairs of electrons producing superconductivity. Section 1.2 Extraction and Use. After an oil drilling operation in 1903 in Dexter, Kansas produced a gas geyser that would not burn, Kansas State geologist Erasmus Hayworth collected samples of the escaping gas and took them back to the University of Kansas at Lawrence, where, with the help of chemists Hamilton Cady and David McFarland, he discovered that the gas consisted of, by volume, 72% nitrogen, 15% methane, a combustible percentage only with sufficient oxygen, 1% hydrogen, and 12% an unidentifiable gas. With further analysis, Cady and McFarland discovered that 1.84% of the gas sample was helium. This showed that despite its overall rarity on Earth, helium was concentrated in large quantities under the American Great Plains, available for extraction as a byproduct of natural gas. The greatest reserves of helium were in the Hugoton and nearby gas fields in southwest Kansas and the panhandles of Texas and Oklahoma. This enabled the United States to become the world's leading supplier of helium. Following a suggestion by Sir Richard Threlfall, the United States Navy sponsored 3 small experimental helium production plants during World War I. The goal was to supply barrage balloons with a non-flammable, lighter-than-air gas. A total of 200,000 cubic feet, or 5,700 cubic meters, of 92% helium was produced in the program, even though only a few cubic feet, less than 100 liters, of the gas had previously been obtained. Some of this gas was used in the world's first helium-filled airship, the U.S. Navy's C-7, which flew its maiden voyage from Hampton Roads, Virginia, to Bowling Field in Washington, D.C. on December 1, 1921. Although the extraction process using low-temperature gas liquefaction was not developed in time to be significant during World War I, production continued. Helium was primarily used as a lifting gas in lighter-than-air craft. This use increased demand during World War II, as well as demands for shielded arc welding. The helium mass spectrometer was also vital in the atomic bomb Manhattan Project. The government of the United States set up the National Helium Reserve in 1925 at Amarillo, Texas, with the goal of supplying military airships in time of war and commercial airships in peacetime. Due to a U.S. military embargo against Germany that restricted helium supplies, the Hindenburg was forced to use hydrogen as the lift gas. Helium use following World War II was depressed, but the reserve was expanded in the 1950s to ensure a supply of liquid helium as a coolant to create oxygen, hydrogen, rocket fuel, among other uses, during the space race and Cold War. Helium use in the United States in 1965 was more than 8 times the peak wartime consumption. After the Helium Acts Amendments of 1960, Public Law 86-777, the U.S. Bureau of Mines arranged for 5 private plants to recover helium from natural gas. For this helium conservation program, the Bureau built a 425-mile or 684-kilometer pipeline from Bushton, Kansas, to connect those plants with the government's partially depleted Cliffside gas field near Amarillo, Texas. This helium-nitrogen mixture was injected and stored in the Cliffside gas field until needed, when it was then further purified. By 1995, 1 billion cubic meters of the gas had been collected, and the reserve was $1.4 billion in debt, prompting the Congress of the United States in 1996 to phase out the reserve. The resulting Helium Privatization Act of 1996, Public Law 104-273, directed the United States Department of the Interior to start emptying the reserve by 2005. Helium produced between 1930 and 1945 was about 98.3% pure, 2% nitrogen, which was adequate for airships. In 1945, a small amount of 99.9% helium was produced for welding use. By 1949, commercial quantities of grade A 99.95% helium were available. For many years, the United States produced over 90% of commercially usable helium in the world, while extraction plants in Canada, Poland, Russia, and other nations produced the remainder. In the mid-1990s, a new plant in Arzew, Algeria, producing 600 million cubic feet, or 1.7 times 10 to the 7th cubic meters, began operation, with enough production to cover all of Europe's demand. Meanwhile, by 2000, the consumption of helium within the U.S. had risen to above 15,000 metric tons. In 2004 to 2006, 2 additional plants, one in Roslafen, Qatar, and the other in Skidka, Algeria, were built. But as of early 2007, Roslafen is functioning at 50%, and Skidka has yet to start up. Algeria quickly became the second leading producer of helium. Through this time, both helium consumption and the cost of producing helium increased. In the 2002 to 2007 period, helium prices doubled, and during 2008 alone, the major suppliers raised prices about 50%. Section 2, Characteristics. Section 2.1, the helium atom. There is a main article about the helium atom. Helium is the next simplest atom to solve using the rules of quantum mechanics after the hydrogen atom. Helium is composed of 2 electrons in orbit around a nucleus containing 2 protons along with some neutrons. However, as in Newtonian mechanics, no system consisting of more than 2 particles can be solved with an exact analytical mathematical approach. See the 3-body problem. And helium is no exception. Thus, numerical mathematical methods are required even to solve the system of 1 nucleus and 2 electrons. The hydrogen atom quantum model has been used extensively to aid in solving the helium atom. The Niels Bohr model of the atom gave a very accurate explanation of the hydrogen atom, but when it came to helium, it collapsed. Werner Heisenberg developed a modification of Bohr's analysis, but it involved half integral values for the quantum numbers. Thomas Fermi theory, also known as density functional theory, is used to obtain the ground state energy levels of the helium atom along with the Hartree-Fock method. These methods have been used to create a quantum mechanical picture of helium electron binding, which is accurate to within less than 2% of the correct value within a few numerical approximation steps. In such a model, various influences must be taken account of, including the electric repulsion of the electrons for each other, and the fact that one electron will, in part, screen the charge of the nucleus for the other. In the case of helium, it has been found that the effective nuclear charge Z, which the electron sees, is about 1.69 units, not the 2 charges of a classic bare helium nucleus. The nucleus of the helium-4 atom, which is identical with an alpha particle, is particularly interesting, inasmuch as high-energy electron scattering experiments show its charge to decrease exponentially from a maximum at a central point, exactly as does the charge density of helium's own electron cloud. The reason for this symmetry is elegant. The pair of neutrons and pair of protons in helium's nucleus both obey exactly the same quantum mechanical rules as do helium's pair of electrons, although the nuclear particles are subject to a different nuclear binding potential, so that all of these fermions fully occupy 1s orbitals in pairs, none of them possessing orbital angular momentum, and each canceling the other's intrinsic spin. This arrangement is energetically extremely stable for all these particles, and this stability accounts for many crucial facts regarding helium in nature. For example, the stability and low energy of the electron cloud state in helium accounts for the element's chemical inertness, the most extreme of all the elements, and also its lack of helium atoms with themselves, producing the lowest melting and boiling points of all the elements. In a similar way, the particular energetic stability of the helium-4 nucleus, produced by similar effects, accounts for the ease of helium-4 production in atomic reactions involving both heavy particle emission and fusion. The stability of helium-4 is the reason hydrogen is converted to helium-4, not deuterium or helium-3 or heavier elements in the Sun. It is also responsible for the fact the alpha particle is by far the most common type of baryonic particle to be ejected from the atomic nuclei. That is, alpha decay is far more common than cluster decay. The unusual ability of the helium-4 nucleus is also important cosmologically. It explains the fact that in the first few minutes after the Big Bang, as the soup of free protons and neutrons which had been created in about a 6-to-1 ratio cooled to the point that nuclear binding was possible, the first nuclei to form were helium-4 nuclei. So tight was helium-4 binding, in fact, that it consumed nearly all of the free neutrons before they could beta decay, leaving very few left to form any lithium, beryllium, or boron. Helium-4 nuclear binding is stronger than in any of these elements. See nucleogenesis and binding energy. And thus, no energetic drive was available once helium had been formed to make elements 3, 4, and 5. It was barely energetically favorable for helium to fuse into the next element with a lower energy per nucleon, carbon. However, due to lack of intermediate elements, this process would take 3 helium nuclei striking each other nearly simultaneously. See triple alpha process. There was no time for significant carbon to be formed in the Big Bang before the early expanding universe cooled in a matter of minutes to the temperature and pressure point where helium fusion to carbon was no longer possible. This left the early universe with a very similar ratio of hydrogen to helium as is seen today, 3 parts hydrogen to 1 part helium-4 by mass. With nearly all the neutrons in the universe, even as it exists today, trapped in the helium-4. All heavier elements, including those necessary for rocky planets like the Earth and for carbon-based or other life, have thus had to be created since the Big Bang, in stars which were hot enough to burn not just hydrogen, for this produces only more helium, but hot enough to burn helium itself. Such stars are massive and therefore rare, and this fact accounts for the fact that all other chemical elements after hydrogen and helium today account for only 2% of the mass of the atomic matter in the universe. Helium-4, by contrast, makes up about 23% of the universe's ordinary matter, nearly all the ordinary matter which isn't hydrogen. Section 2.2, Gas and Plasma Phases. Helium is the least reactive noble gas after neon, and thus the second least reactive of all elements. It is inert and monatomic in all standard conditions. Due to helium's relatively low molar atomic mass, in the gas phase its thermal conductivity, specific heat, and sound speed are all greater than any other gas except hydrogen. For similar reasons, and also due to the small size of helium atoms, helium's diffusion rate through solids is 3 times that of air and around 65% that of hydrogen. Helium is less water-soluble than any other gas known, and helium's index of refraction is closer to unity than that of any other gas. Helium has a negative Joule-Thomson coefficient at normal ambient temperatures, meaning it heats up when allowed to freely expand. Only below its Joule-Thomson inversion temperature of about 32 to 50 Kelvin at 1 atmosphere does it cool upon free expansion. Once pre-cooled below this temperature, helium can be liquefied through expansion cooling. Most extraterrestrial helium is found in a plasma state, with properties quite different from those of atomic helium. In a plasma, helium's electrons are not bound to its nucleus, resulting in very high electrical conductivity, even when the gas is only partially ionized. The charged particles are highly influenced by magnetic and electric fields. For example, in the solar wind, together with ionized hydrogen, the particles interact with the Earth's magnetosphere, giving rise to Birkeland currents and the aurora. Section 2.3, Solid and Liquid Phases. Also see main article, Liquid Helium. Unlike any other element, helium will remain liquid down to absolute zero at normal pressures. This is a direct effect of quantum mechanics. Specifically, the zero-point energy of the system is too high to allow freezing. Solid helium requires a temperature of 1 to 1.5 Kelvin, about negative 272 degrees Celsius, or negative 457 degrees Fahrenheit, and about 25 bar or 2.5 megapascals of pressure. It is often hard to distinguish solid from liquid helium since the refractive index of the two phases are nearly the same. The solid has a sharp melting point and has a crystalline structure, but it is highly compressible. Applying pressure in a laboratory can decrease its volume by more than 30%. With a bulk modulus on the order of 5 times 10 to the 7th pascals, it is 50 times more compressible than water. Solid helium has a density of 0.214 plus or minus 0.006 of a gram per milliliter at 1.15 Kelvin and 66 atmospheres. The projected density at 0 Kelvin and 25 bar is 0.187 plus or minus 0.009 of a gram per milliliter. Section 2.3.1, Helium-1 state. Below its boiling point of 4.22 Kelvin and above the lambda point of 2.1768 Kelvin, the isotope helium-4 exists in a normal, colorless liquid state called helium-1. Like other cryogenic liquids, helium-1 boils when it is heated and contracts when its temperature is lowered. Below the lambda point, however, helium doesn't boil, and it expands as the temperature is lowered further. Helium-1 has a gas-like index of refraction of 1.026, which makes the surface so hard to see that floats of styrofoam are often used to show where the surface is. This colorless liquid has a very low viscosity and a density 1/8 that of water, which is only 1/4 the value expected from classical physics. Quantum mechanics is needed to explain this property, and thus both types of liquid helium are called quantum fluids, meaning they display atomic properties on a macroscopic scale. This may be an effect of its boiling point being so close to absolute zero, preventing random molecular motion, or thermal energy, from masking the atomic properties. Section 2.3.2 Helium-2 state. Liquid helium below its lambda point begins to exhibit very unusual characteristics in a state called Helium-2. Boiling of Helium-2 is not possible due to its high thermal conductivity. Heat input instead causes evaporation of the liquid directly to gas. The isotope Helium-3 also has a superfluid phase, but only at much lower temperatures. As a result, less is known about such properties in the isotope Helium-3. Helium-2 is a superfluid, a quantum mechanical state of matter with strange properties. For example, when it flows through capillaries as thin as 10 to the negative 7th to 10 to the negative 8th meters, it has no measurable viscosity. However, when measurements were done between two moving disks, a viscosity comparable to that of gaseous helium was observed. Current theory explains this using the two-fluid model for Helium-2. In this model, liquid helium below the lambda point is viewed as containing a proportion of helium atoms in a ground state, which are superfluid and flow with exactly zero viscosity, and a proportion of helium atoms in an excited state, which behave more like an ordinary fluid. In the fountain effect, a chamber is constructed which is connected to a reservoir of Helium-2 by a centered disk through which the superfluid helium leaks easily, but through which non-superfluid helium cannot pass. If the interior of the container is heated, the superfluid helium changes to non-superfluid helium. In order to maintain the equilibrium fraction of superfluid helium leaks through and increases the pressure, causing liquid to fountain out of the container. The thermal conductivity of Helium-2 is greater than that of any other known substance, 1,000,000 times that of Helium-1 and several hundred times that of copper. This is because heat conduction occurs by an exceptional quantum mechanical mechanism. Most materials that conduct heat well have a valence band of free electrons which serve to transfer the heat. Helium-2 has no such valence band, but nevertheless conducts heat well. The flow of heat is governed by equations that are similar to the wave equation used to characterize sound propagation in air. When heat is introduced, it moves at 20 meters per second at 1.8 Kelvin through Helium-2 as waves in a phenomenon known as second sound. Helium-2 also exhibits a creeping effect. When a surface extends past the level of Helium-2, the Helium-2 moves along the surface, seemingly against the force of gravity. Helium-2 will escape from a vessel that is not sealed by creeping along the sides until it reaches a warmer region where it evaporates. It moves in a 30 nanometer thick film regardless of surface material. This film is called a Rollin film and is named after the man who first characterized this trait, Bernard V. Rollin. As a result of this creeping behavior and Helium-2's ability to leak rapidly through tiny openings, it is very difficult to confine liquid helium. Unless the container is carefully constructed, the Helium-2 will creep along the surfaces and through the valves until it reaches somewhere warmer, where it will evaporate. Waves propagating across a Rollin film are governed by the same equation as gravity waves in shallow water. But rather than gravity, the restoring force is the van der Waals force. These waves are known as third sound. Section 3. Isotopes. See also the main article, Isotopes of Helium. There are 8 known isotopes of helium, but only helium-3 and helium-4 are stable. In the Earth's atmosphere, there is 1 helium-3 atom for every million helium-4 atoms. Unlike most elements, helium's isotopic abundance varies greatly by origin due to the different formation processes. The most common isotope, helium-4, is produced on Earth by alpha decay of heavier radioactive elements. The alpha particles that emerge are fully ionized helium-4 nuclei. Helium-4 is an unusually stable nucleus because its nucleons are arranged into complete shells. It was also formed in enormous quantities during Big Bang nucleosynthesis. Helium-3 is present on Earth only in trace amounts, most of it since Earth's formation, though some falls to Earth trapped in cosmic dust. Trace amounts are also produced by the beta decay of tritium. Rocks from the Earth's crust have isotope ratios varying by as much as a factor of 10, and these ratios can be used to investigate the origin of rocks and the composition of the Earth's mantle. Helium-3 is much more abundant in stars as a product of nuclear fusion. Thus, in the interstellar medium, the proportion of helium-3 to helium-4 is around 100 times higher than on Earth. Extraplanetary material, such as lunar and asteroid regolith, have trace amounts of helium-3 from being bombarded by solar winds. The Moon's surface contains helium-3 at concentrations on the order of 1/100th part per million. A number of people, starting with Gerald Kulsinski in 1986, have proposed to explore the Moon, mine lunar regolith, and use the helium-3 for fusion. Liquid helium-4 can be cooled to about 1 Kelvin using evaporative cooling in a 1K pot. Similar cooling of helium-3, which has a lower boiling point, can achieve about 2/10 Kelvin in a helium-3 refrigerator. Equal mixtures of liquid helium-3 and helium-4 below 8/10 Kelvin separate into 2 immiscible phases due to their dissimilarity. They follow different quantum statistics. Helium-4 atoms are bosons, while helium-3 atoms are fermions. Dilution refrigerators use this immiscibility to achieve temperatures of a few millikelvins. It is possible to produce exotic helium isotopes which rapidly decay into other substances. The shortest-lived heavy helium isotope is helium-5, with a half-life of 7.6 times 10 to the negative 22nd seconds. Helium-6 decays by emitting a beta particle and has a half-life of 8/10 seconds. Helium-7 also emits a beta particle as well as a gamma ray. Helium-7 and helium-8 are created in certain nuclear reactions. Helium-6 and helium-8 are known to exhibit a nuclear halo. Helium-2, 2 protons, no neutrons, is a radioisotope that decays by proton emission into a protium with a half-life of 3 times 10 to the negative 27th seconds. Section 4. Compounds. See also noble gas compounds. Helium is chemically unreactive under all normal conditions due to its valence of 0. It is an electrical insulator unless ionized. As with the other noble gases, helium has metastable energy levels that allow it to remain ionized in an electrical discharge with a voltage below its ionization potential. Helium can form unstable compounds, known as excimers, with tungsten, iodine, fluorine, sulfur, and phosphorus when it is subjected to an electric glow discharge through electron bombardment or is otherwise a plasma. Hene, HgHe10, WHe2, and the molecular ions He2+, He2, 2+, HeH+, and Hed+ have been created this way. This technique has also allowed the production of the neutral molecule He2, which has a large number of band systems, and HgHe, which is apparently only held together by polarization forces. Theoretically, other true compounds may also be possible, such as helium fluorohydride, HHEF, which would be analogous to HARF, discovered in 2000. Calculations show that two new compounds containing a helium-oxygen bond could be stable. The two molecular species predicted using theory, CSFHEO and NCH3,4 FHEO, are derivatives of a metastable FHEO ion first theorized in 2005 by a group from Taiwan. If confirmed by experiment, such compounds will end helium's chemical nobility, and the only remaining noble element will be neon. Helium has been put inside the hollow carbon cage molecules, the fullerenes, by heating under high pressure. The endohedral fullerene molecules formed are stable up to high temperatures. When chemical derivatives of these fullerenes are formed, the helium stays inside. If helium-3 is used, it can be readily observed by helium nuclear magnetic resonance spectroscopy. Many fullerenes containing helium-3 have been reported. Although the helium atoms are not attached by covalent or ionic bonds, these substances have distinct properties and a definite composition, like all stoichiometric chemical compounds. Section 5. Occurrence and Production. Section 5.1. Natural Abundance. Helium is the second most abundant element in the known universe after hydrogen, constituting 23% of the baryonic mass of the universe. The vast majority of helium was formed by Big Bang nucleosynthesis from 1 to 3 minutes after the Big Bang. As such, measurements of its abundance contribute to cosmological models. In stars, it is formed by the nuclear fusion of hydrogen in proton-proton chain reactions and the CNO cycle, part of stellar nucleosynthesis. In the Earth's atmosphere, the concentration of helium by volume is only 5.2 parts per million. The concentration is low and fairly consistent, despite the continuous production of new helium, because most helium in the Earth's atmosphere escapes into space by several processes. In the Earth's heterosphere, a part of the upper atmosphere, helium and other lighter gases are the most abundant elements. Nearly all helium on Earth is a result of radioactive decay, and thus an earthly helium balloon is essentially a bag of retired alpha particles. Helium is found in large amounts in minerals of uranium and thorium, including cleveites, pitchblende, carnotite, and monazite, because they emit alpha particles, helium nuclei, or He2+, to which electrons immediately combine as soon as the particle is stopped by the rock. In this way, an estimated 3,000 tons of helium are generated per year throughout the lithosphere. In the Earth's crust, the concentration of helium is 8 parts per billion. In seawater, the concentration is only 4 parts per trillion. There are also small amounts in mineral springs, volcanic gas, and meteoric iron. Because helium is trapped in a similar way by non-permeable layer of rock like natural gas, the greatest concentrations on the planet are found in natural gas, from which most commercial helium is derived. The concentration varies in a broad range from a few parts per million up to over 7% in a small gas field in San Juan County, New Mexico. Section 5.2, Modern Extraction. For large-scale use, helium is extracted by fractional distillation from natural gas, which contains up to 7% helium. Since helium has a lower boiling point than any other element, low temperature and high pressure are used to liquefy nearly all the other gases, mostly nitrogen and methane. The resulting crude helium gas is purified by successive exposures to lowering temperatures, in which almost all the remaining nitrogen and other gases are precipitated out of the gaseous mixture. Activated charcoal is used as a final purification step, usually resulting in 99.995% pure grade A helium. The principal impurity in grade A helium is neon. In a final production step, most of the helium that is produced is liquefied via a cryogenic process. This is necessary for applications requiring liquid helium and also allows helium suppliers to reduce the cost of long-distance transportation, as the largest liquid helium containers have more than 5 times the capacity of the largest gaseous helium tube trailers. In 2005, approximately 160 million cubic meters of helium were extracted from natural gas or withdrawn from helium reserves, with approximately 83% from the United States, 11% from Algeria, and most of the remainder from Russia and Poland. In the United States, most helium is extracted from natural gas of the Hugoton and nearby gas fields in Kansas, Oklahoma, and Texas. Diffusion of crude natural gas through special semi-permeable membranes and other barriers is another method to recover and purify helium. Helium can be synthesized by bombardment of lithium or boron with high-velocity protons, but this is not an economically viable method of production. Section 6. Applications. Helium is used for many purposes that can require some of its unique properties, such as its low boiling point, low density, low solubility, high thermal conductivity, or inertness. Helium is commercially available in either liquid or gaseous form. As a liquid, it can be supplied in small containers called dewars, which hold up to 1,000 liters of helium, or in large ISO containers, which have nominal capacities as large as 11,000 gallons, or 41,637 liters. In gaseous form, small quantities of helium are supplied in high-pressure cylinders holding up to 300 standard cubic feet, while large quantities of high-pressure gas are supplied in tube trailers which have capacities of up to 180,000 standard cubic feet. Airships, balloons, and rocketry. Because it is lighter than air, airships and balloons are inflated with helium for lift. While hydrogen gas is approximately 7% more buoyant, helium has the advantage of being non-flammable, in addition to being fire retardant. In rocketry, helium is used as an ullage medium to displace fuel and oxidizers in storage tanks and to condense hydrogen and oxygen to make rocket fuel. It is also used to purge fuel and oxidizer from ground support equipment prior to launch and to pre-cool liquid hydrogen in space vehicles. For example, the Saturn V booster used in the Apollo program needed about 13 million cubic feet or 370,000 cubic meters of helium to launch. Commercial and recreational. Helium alone is less dense than atmospheric air, so it will change the timbre, not the pitch, of a person's voice when inhaled. However, inhaling it from a typical commercial source, such as that used to fill balloons, can be dangerous due to the risk of asphyxiation from lack of oxygen and the number of contaminants that may be present. These could include trace amounts of other gases in addition to aerosolized lubricating oil. For its low solubility in nervous tissue, helium mixtures such as Trimix, Heliox, and Heliair are used for deep diving to reduce the effects of narcosis. At depths below 150 meters, or 490 feet, small amounts of hydrogen are added to a helium-oxygen mixture to counter the effects of high-pressure nervous syndrome. At these depths, the low density of helium is found to considerably reduce the effort of breathing. Helium neon lasers have various applications, including barcode readers. Industrial. For its inertness and high thermal conductivity, neutron transparency, and because it does not form radioactive isotopes under reactor conditions, helium is used as a heat transfer medium in some gas-cooled nuclear reactors. Helium is used as a shielding gas in arc welding processes on materials that are contaminated easily by air. Helium is used as a protective gas in growing silicon and germanium crystals, in titanium and zirconium production, and in gas chromatography because it is inert. Because of its inertness, thermally and calorically perfect nature, high speed of sound, and high value of the heat capacity ratio, it is also useful in supersonic wind tunnels and impulse facilities. Because it diffuses through solids at 3 times the rate of air, helium is used as a tracer gas to detect leaks in high vacuum equipment and high pressure containers. Helium, mixed with a heavier gas such as xenon, is useful for thermoacoustic refrigeration due to the resulting high heat capacity ratio and low Prandtl number. The inertness of helium has environmental advantages over conventional refrigeration systems which contribute to ozone depletion or global warming. Scientific. The use of helium reduces the distorting effects of temperature variations in the space between lenses in some telescopes due to its extremely low index of refraction. This method is especially used in solar telescopes where a vacuum-tight telescope tube would be too heavy. The age of rocks and minerals that contain uranium and thorium can be estimated by measuring the level of helium with a process known as helium dating. Liquid helium is used to cool certain metals to the extremely low temperatures required for superconductivity, such as in superconducting magnets for magnetic resonance imaging. The Large Hadron Collider at CERN uses 96 tons of liquid helium to maintain the temperature at 1.9 Kelvin. Helium at low temperatures is also used in cryogenics. Helium is a commonly used carrier gas for gas chromatography. Section 7. Safety. Neutral helium at standard conditions is non-toxic, plays no biological role, and is found in trace amounts in human blood. If enough in helium is inhaled that oxygen needed for normal respiration is replaced, asphyxia is possible. The safety issues for cryogenic helium are similar to those of liquid nitrogen. Its extremely low temperatures can result in cold burns, and the liquid-to-gas expansion ratio can cause explosions if no pressure relief devices are installed. Containers of helium gas at 5 to 10 Kelvin should be handled as if they contain liquid helium, due to the rapid and significant thermal expansion that occurs when helium gas at less than 10 Kelvin is warmed to room temperature. Section 8. Biological effects. The human voice is not like a string instrument, in which the primary vibrating object completely sets the pitch of the sound. Rather, in a human, the vocal folds act as a source of polytonic vibration, much like the reeds in woodwind instruments. As in a woodwind, the size of the resonant cavity plays a large part in picking out and amplifying a given fundamental or overtone frequency of vibration during sound making. The voice of a person who has inhaled helium temporarily changes in timbre in a way that makes it sound high-pitched, because higher overtones are being amplified. The speed of sound in helium is nearly 3 times the speed of sound in air. Because the fundamental frequency of a gas-filled cavity is proportional to the speed of the sound in gas, when helium is inhaled, there is a corresponding increase in the pitch of the resonant frequencies of the vocal tract. The opposite effect, lowering frequencies, can be obtained by inhaling a dense gas such as sulfur hexafluoride. Inhaling helium can be dangerous if done to excess, since helium is a simple asphyxiant and so displaces oxygen needed for normal respiration. Breathing pure helium continuously causes death by asphyxiation within minutes. Inhaling helium directly from pressurized cylinders is extremely dangerous, as the high flow rate can result in barotrauma, fatally rupturing lung tissue. However, death caused by helium is quite rare, with only 2 fatalities reported between 2000 and 2004 in the United States. At high pressures, more than about 20 atmospheres, or 2 megapascals, a mixture of helium and oxygen, heliox, can lead to a high-pressure nervous syndrome, a sort of reverse anesthetic effect. Adding a small amount of nitrogen to the mixture can alleviate the problem.